Okay, so hello everyone. I am Daniele de Sensi from Sapienza University of Rome, and this is a joint work with Tommaso and Torsten from ETH Zurich and David from Aachen University. So if I had to summarize this work in one sentence, I would say that Swing is a novel algorithm for running Allreduce, Allgather, and Reduce Cutter, specifically optimized for multidimensional torus networks. So even though one important disclaimer is that even though the work is focused on torus networks, we expect actually advantages on any kind of blocking network. So this is something that we didn't prove it yet, but we are fairly confident this should also help on other type of networks. So, and why do we focus on torus? And the main reason for that is deep learning. Okay, so why are we interested in Allreduce, and why are we interested specifically in torus networks? So the main reason is that if we analyze the way in which communication happens during distributed deep learning training, we can basically see that most of the communication is nearest neighbor communication. Usually you have this kind of three-level parallelism where you have data parallelism, pipeline parallelism, and operator parallelism. And if we analyze, I will not go into the details, but if we analyze the way in which these communications are arranged on a logical topology, let's say, we can see that this basically maps one-to-one with the 3D torus. And so that's the reason why we're interested in this kind of networks, which have a lower bisection bandwidth than, for example, non-blocking FAT3, but usually are good enough for running this kind of workloads. So just one, as a side note, so this is why people are like investing and researching on topology design specifically tailored for such kind of workload. And this is just an example. This is Hamming mesh, which is a new topology which was proposed a few years back, which is basically like a torus with some extra links to improve the bisection bandwidth and say reduce the overhead for running this kind of workloads. Now, this is something which also happened in the industry. So we have been witnessing several architectures tailored for deep learning training, which are actually based on torus. And this is the example of Google TPUs, which is based on a 3D torus, but also AWS Trainium and GraphCore IPU, which are based on 2D torus. So this is kind of an old-fashioned topology, which is becoming popular again now due to this kind of workloads. So that's why we focus on torus, and also why we focus on Allreduce, because that's one of the most important communication kernels, let's say, that are executed during the training of these workloads. Now, what's the state of the art regarding Allreduce algorithms in torus networks? There are basically three main algorithms. I'll just describe here two of them. You will find the third one in the paper, but it's usually only useful for some corner cases. Why can't we just run any existing Allreduce algorithm? And the reason is that the torus has such a low bisection bandwidth, which means that it's very important to have algorithms designed for that specific topology. So we can just take any algorithm for Allreduce and run it on a torus, because most likely it will perform poorly. So, and in describing this state-of-the-art algorithms, I will consider three characteristics, let's say, to characterize them. The first one is how many steps the algorithm perform. So usually these collective algorithms, they execute a number of steps, one after the other. And the more steps you have, the higher will be, the lower will be the higher will be the runtime, especially for small vectors. The other thing, which is particularly important on multidimensional torus networks, is whether the algorithm can send and receive data from all the different directions at the same time. So imagine that this is like a 2D torus. it's important that the algorithm can exploit, let's say, all the 4 directions at the same time, rather than just sticking to one. Otherwise, you will not fully exploit your available network bandwidth. And the last one, which is often overlooked, is how many flows or how many messages will be forwarded on the same link or on the same path, which is particularly relevant for networks which are blocking networks like it is the case for Torus. So now the first algorithm I'm going to describe is the bucket algorithm, which dates back around to 2010, more or less. And this is, I mean, I will not describe how the algorithm works. It's just to give you an idea what are the performance characteristics of those algorithms. So the bucket algorithm performs a number of steps, which is linear in the number of nodes that you have in each dimension, which is not good because it means that the larger the network is, the higher the number of steps. And this will scale linearly with the network size, which means that for very small messages, the performance will not be really good. But the good thing is that they can use all the ports, all the network ports simultaneously. So they can send and receive data on all the 4 directions in case of a 2D torus at the same time. And the other good thing is that there are no flow collisions. So each link in the network is usually traversed by at most one message. So which means that basically you can inject data at full bandwidth. So that's the first algorithm. The second algorithm is recursive doubling. So this is a specific variant of recursive doubling, which has been optimized for multidimensional torus networks. And in this case, the main advantage is that it can run in a number of steps, which is logarithmic in the number of nodes. So this is particularly good when you have very large networks or when you have small messages, because the impact of the latency factor, let's say, will be smaller. The issue is that it can only use one network port at a time, which means that basically in the case of a 2D torus, you will just use 1/4 of your available network bandwidth, which is not good. And the other thing is that it also introduces many flow collisions. I will show this more in detail later. But the idea here is that many messages at some point will be forwarded on one single link, which means that the bandwidth of that link will be shared across several flows. Okay, so what's Swing? So that's the state of the art again. So with Swing, we try to take the best of the 2 worlds and having something which kind of improves over the state of the art. So we design an algorithm which is logarithmic in the number of nodes. It uses all the network ports simultaneously, so it can fully exploit the available bandwidth, and it just has a few flow collisions. Now, describing the details of the algorithm, it's not easy to do in a presentation. So I will just try to give a general intuition about how this works, and then you can find all the details in the paper. So let me start from this point. So how do we reduce flow collision? Okay, so this is the main intuition behind this algorithm, and it's one of the reasons why we will be able to outperform the state of the art. So, and to explain this, I will show you how this differs from recursive doubling with a simple example. Okay, so we have recursive doubling and we have Swing, and I will go step by step. Okay, so let's imagine that you have a 1D torus. So it's basically a ring. It's a ring with 16 nodes in this case. So in the first step, what recursive doubling does is that basically each node exchanges data with a node at distance 1. So 0 and 1 will communicate, 2 and 3 will communicate, and so on and so forth. So what Swing does, first step, it's exactly the same. Okay, so far they are behaving the same. Then second step. So at second step is where issues starts to arise. So in this case, at step 1, each node communicates with the node at distance 2, which means that 0 communicates with 2 and 1 communicates with 3. And the issue here now is that since this is a ring network, this link here will be shared by 2 different flows. So this link will be shared both by the message being forwarded from 0 to 2 and by the message being forwarded from 1 to 3. So now if this is, for example, a 100 gigabit per second link, it means now that those 100 gigabit per second, so 50 gigabit per second will be used for the communication between 1 and 3, and 50 gigabit for the communication between 0 and 2. So it means that if one link is shared by n different flows, each node will be able to inject the data only at 1 divided by n, the injection bandwidth, which is bad, right? Here, basically, it means that the nodes are injecting at half of their actual injection bandwidth, which means that this step will take basically twice as long to complete compared to the previous one. So what do we do in Swing? In the second step, we, instead of talking with the node at distance at distance 2, we still talk with the node at distance 1, but on the other direction. Now, of course, we cannot do this just randomly. Okay, so the way in which we select which node must be talking to whom must be done in such a way that eventually the algorithm is still correct. So we cannot just take random numbers and hope that this works. Okay, but I'm not going to discuss why this is correct and why this works. You can find all the detail in the paper. But this is the intuition. The intuition is that we try to select the communication peers in such a way that we minimize the distance between communicating nodes. And by minimizing the distance, we minimize the number of flows that share the same link, and thus we maximize the injection bandwidth. So that's the basic intuition. Okay, so then step 2, recursive doubling. In recursive doubling, nodes communicate with nodes at distance 4, which means that there is one single link being used by 4 flows, which means that all the nodes will inject at 1/4 of their injection bandwidth. With Swing, instead, we communicate with nodes at distance 3, and we communicate it in such a way that some of them will communicate to the right, some of them will communicate towards the left, and eventually we have that the most congested link is just used by 2 flows at a time. And this will proceed for a number of steps, and eventually we have the correct result. Again, you will find all the details about how this thing is, how the nodes are selected and why this works in the paper. But this is the main intuition, right? So we just want to minimize the distance between communicating nodes. In the paper, you will find also the proof of correctness and the generalization to D dimensions. I just show here the example with one single dimension, so basically a ring, but this can be generalized. This is actually generalized to n dimension, to D dimensions. Okay, so that's how we managed to reduce the flow collisions, how to use all the network ports simultaneously. And again, I will show this with an example. So let's suppose that we have a 2D torus. In this case, it's a 4x4 torus. And the idea here is just to execute the algorithm on one dimension at a time. So I first execute the algorithm on the x-axis, then on the y-axis, and so on and so forth. And they keep swapping between these 2 directions. Now I have what the algorithm does is that if I have 2 dimensions and thus 4 network ports, okay, so 0 has 1 network port towards 1 network port towards 4, 1 towards 12, and 1 towards 3. So 4 possible directions for injecting traffic. So the algorithm takes your vector, it splits the vector into 4 parts, and on each of these 4 parts will run an independent Allreduce algorithm. Okay, so I have one Allreduce aggregating the first part of the vector, so 1/4 of the data, another Allreduce algorithm running on the second part, and so on and so forth. So 4 independent Allreduce running on 4 parts of the original data. How do they run? So the first one just runs plainly as I shown before. Okay, so now I want, for the second part, I don't want to use again this network port. I would like to use one of the other. So what I do is basically I logically transpose the network. So I transpose this kind of 2D torus, and they run the same algorithm again. Okay, so the algorithm tells you that you need to communicate with the node at distance 1 on the x-axis. Okay, and that's what's happening. It's just that I logically, let's say, rearrange the ranks in such a way that now I can use the other network port. And I do the same. So to use the other 2 missing ports, what do? I shift the columns by 1. So basically, I logically rotate my network, and I apply the same algorithm again. So now I can also communicate with node 3. And for the last port, I transpose it, and I shift the columns by 1. So again, the intuition here is that I want to run exactly the same algorithm, but on logically transposed and rotated version of the network in such a way that eventually I use all the 4 directions that I have. And this, of course, can be generalized in any dimensions. Again, this is just a visual intuition of it, but you can find the details in the paper. So, and this is what allows us to use all the network ports simultaneously. Okay, so now we see the full picture, and what we see is that the main advantage of Swing is that it's logarithmic in the number of nodes, which means that we expect it to be fairly good for small messages. It uses all the network ports simultaneously, so it should also be fairly good for large messages. But it has few flow collisions. Okay, and we will see that this is gonna be an issue only for very, very large messages. So I think it was starting from like 512 megabytes. But otherwise, like from 1 byte to a few hundred megabytes, we expect Swing to outperform the other 2 algorithms. So how do we do that? So how do we evaluate Swing to see what happens in practice? So we run a bunch of simulations using the SST packet level network simulator by simulating networks with 400 gigabit per second links and 100 nanosecond latency for crossing the switch. And then we simulate 300 nanosecond per hop latency. So sorry, 100 nanosecond latency on the link, 300 nanosecond to cross one single hop. Okay, I'll show you some kind of aggregated data. You can find in the paper more details. But so what I want to show here is, so on the x-axis we have the Allreduce size. So how large is the vector that we want to reduce? On the y-axis we have the performance gain of Swing compared to the best state-of-the-art algorithm. Okay, so we run the state-of-the-art algorithms, we pick the most performing one, and then we show the advantage of Swing compared to that algorithm. And we start with a fairly small network, like an 8x8 torus with 64 nodes. And we can see this kind of trend where basically the performance, it's always better compared to the state of the art, except that for very large messages. And this is something that somewhat we expected. Again, we did some cost modeling. You can find the details in the paper, but this was fairly expected. And the reason for that is that since we still have a few flow collisions, it means that at some point we will still have some overhead on the bandwidth term of our model, which means that for very large messages we are going to see some performance drop. And usually we get the best advantage like in the middle range. So like for medium-sized messages, that's where we expect the algorithm to outperform significantly the other ones, like in this case up to 60%. And we did the same for several other. We analyzed basically the scalability as a function of the network size. So we started increasing the network, and then we simulated up to a 16K nodes network, and we observed the same trend over and over. There are a couple of things that happen here. So it's important to notice that in the worst case, we are going to lose like 20% of performance compared to the state of the art, but this only happens for really large messages. But it's also true that, like in the best case, we are able to get more than 2x improvement compared to the state of the art. Okay, so this was basically the scalability as a function of the Allreduce sides and of the network sides. Now, in the paper, there are many more results about all different kinds of network configurations and whatnot. So let me try to summarize this a little bit. Okay, so what that plot on the right represents. So basically, we have all the different configurations that we analyzed here. Okay, so these are exactly the same network size that we have here. But now, instead of showing the entire line, we just show the distribution of those performance gain. Okay, so basically this box plot here contains all the points on the blue line. So it's just a synthetic way to show how much performance gain we expect for that specific scenario. So it's exactly the same data, just represented in a different way. And this is just helpful to be a little bit faster in discussing those results. Okay, so far we have seen square torus networks of different sides. But what happens, for example, when you have a different network bandwidth, right? So we simulated a 400 gigabit per second network, but bandwidth is increasing fast. What if we have a faster network? Are we still gonna have this advantage or not? And the answer is that things actually are going to improve, because when if you have a higher bandwidth, the overhead that you have because of this flow collision is going to be smaller. So eventually, as network bandwidth increase, the relevance of the latency will be higher and higher, which means that the fact that we run in a logarithmic number of steps rather than a linear number of steps is going to be more helpful, which means that for very large network bandwidth, eventually we expect no performance drop compared to the state of the art. And basically, we expect swing to outperform the state of the art regardless of the message size. What about multidimensional networks? Again, if we start increasing the number of dimensions from 2D torus to 3D or 4D, again, things are going to improve, because like, think about it. When you increase the number of dimensions, the diameter of the network will become smaller, which means now that intuitively you perform more communications with nodes that are at a shorter distance, which means that, again, the impact of these flow collisions will be smaller and smaller. So again, when increasing the number of dimensions, performance are gonna get better, and we will outperform state of the art regardless of the message size. What about other topologies, torus-like topologies like Hamming mesh? Again, just to briefly recall it, Hamming mesh is a torus with some extra links. And those extra links help in alleviating this kind of flow collision problem. So you have extra links, so you are able to distribute better the traffic over the network, so you have fewer collisions per link, and thus you have a better performance again. And the last thing I'm gonna discuss is about rectangular torus. So what if the torus is not perfectly a square, but like all dimensions have different sides? Here things get a little bit more complicated. There is quite of some long discussion in the paper on why. But the reason is that this kind of asymmetry across dimension eventually introduces some overhead, because you have some kind of you have to imagine that like the communication is not balanced across all these dimensions. So for example, in the case of swing, at some point you might have not any communication to perform on one dimension, and you will just keep communicating on some of those dimensions, which means that you will not be using all the network ports that you have, simply because you don't have any more nodes to communicate with on one dimension. So eventually this complicates a little bit the thing. So in general, what we observe is that for some scenarios, the maximum performance gain increases by a lot, but for very large messages also we observe some performance drop. Anyway, this was more or less the summary of the results. Of course, for each of these boxes, you can find the actual performance lines in the paper with all the details and the discussion about some of these effects. Okay, so to conclude, Swing it's an algorithm optimized, an all-reduced algorithm. Actually, it also works for reduced scatter and all gather, which is optimized for torus networks. And we say that this is based on two intuitions. The first one is that we reduce the number of collisions happening on each link. And the other one is that we are able to use all the network ports simultaneously. And we show that in practice, this, I mean, we proved this also theoretically with cost modeling, but then we also simulated this on several type of torus and torus-like networks, showing that actually it can provide performance advantages on almost all the message sides and network types, except that for very large messages where we observe some performance drop. So thank you for listening. This concludes my talk.